Assalamu alaikum. Welcome everyone to our Digital Electronics 2 class. In this week, we'll go through the topics oscillators. So this will be the part 1. It will have another part in next week. And before we start our topics, I want to clear one thing that we'll have the term paper in the 12th week. So you will get the questions and the term as our assignment on that week in under week 12, and please prepare before that, and you will get approximately 10 days to complete the assignment or term paper, and please submit it in the due time. So here is the content, and the first one is oscillators, then the op-amp oscillators, phase shift oscillator, that's mean different types of oscillators, wine bridge oscillator, and finally square or triangle function generator. Oscillators. So basically oscillators are signal sources or signal generators. It can generate different signals, different types of signals. These types of signals may have uh, known wave shape, frequency, or amplitude. So we can get that characteristics from generated signal that we need. So for generation of signal, we can also remember that we have some laboratory generated signal. That's mean in laboratory we have some signal generator, but sometimes for others applications we need to generate signal sources to create and receive radio and television signals, or to create electronic music and some other uses. So for that reason, we can use op-amp or some other linear device to produce very low frequencies to very high frequency, and that may be more than 1 gigahertz. It is possible to generate through oscillators. And with employing the op-amps, we can generate the uh, frequency below 1 megahertz. So the different range of frequencies it is possible to generate with the oscillators. And for oscillators, the output shape may be sinusoidal, maybe triangular, pulse, or some other shapes. So we can easily uh, change the output shape by using the op-amp oscillators. So op-amp or operational amplifier can be used as an oscillators when the feedback amplifier having closed loop gain greater than 1. So the closed loop gain AF, if it is greater than 1, and it also if it satisfies the phase condition, that will result in operation as an oscillator circuit. So it will generate the varying output signal. So this varying output signal may be sinusoidally, and if the output is sinusoidal, then it is referred as a sinusoidal oscillators. And if the output later drops quickly to another voltage level, that circuit is generally referred as pulse wave oscillator, or sometimes square wave oscillators. Barkhausen criteria. So for oscillators, it has an important criteria that is called Barkhausen. So how it's known, you can see that this is a amplifier input from one side, another of first stage amplifier stage, then second one is feedback stage, that is beta. A is amplifier and beta is feedback stage. So for the input there is also an there is a switch also. If this switch is open, so no oscillation is occurs. So first we need to consider that there is a voltage and that is Vi. So this will result in output voltage V0, and that is V0 equals to AVI. So after the amplifier stage we have the beta, that's mean the feedback stage. So the output of VF, output of feedback stage, that is beta AVI. VF equals to beta AVI. So if the circuits of the base amplifier and feedback network provide beta A of correct magnitude and phase, that's mean beta A, this value, if it's in magnitude, correct magnitude and in phase, then this VF equals to VI can be made equal. So this VF equals to beta AVI, so this beta A, if beta A is equals to 1, then VF will be equal to VI. So in that case, when the switch is closed and if we remove the VI, then the circuit will continue operating since the feedback voltage is sufficient to drive the amplifier and feedback circuits. So the output from will still exist only when the condition is beta A equals to 1. So this condition is known as the Barkhausen criteria for oscillation. So this Barkhausen criteria may state as follows: in order to maintain self-oscillation, the closed loop gain must be unity or greater, and the loop phase must be in 360 degree. In where the n value would be 0, 1, 2, 3 or some other values. So it must be in 360 degree phase shift. Phase shift oscillators. So considering the Barkhausen criteria, it should be possible to create an oscillator by just using a phase shift network and in the feedback path. So for example, this is the circuit, and you can see that the first part is inverting amplifier, and that will create 180 degree phase shift, minus 180 degree, and if we add additional 180 degrees phase shift in the feedback path, then it will create the oscillation. So the requirement will be only the gain of the inverting amplifier should be greater than the loss produced by the feedback path. Then the self oscillation will create. So for phase shift oscillator, we need to create 180 degree phase shift in its feedback path. So how can we create that path? It is very easy. If we use the RC network in the phase shift path, then we can combine the phase shift of 180 degree. And you can see that from here, this is called RC network or a ladder network. Resistor and capacitor both are here. So R1, C1, R2, C2, R3, C3. So this total 3 stages. Each stage will create 60 degree phase shift. So total 180 degree because of 3 stages. So if we connect this feedback path into the op-amp or inverting op-amp, you see that here, like this one feedback network, it will connect here. So it will create the additional 180 degree phase shift that will create the self oscillation of op-amp. So to get the values of R1, R2, R3, we can set up some values of R1 so that the R2 might be set to 10 times of the value of R1. So something value of R1 and R2 will be 10 times of R1, and R3 will be 10 times the value of R2. So it will increase like 10 times from R1, R2 and R3, and in reversely the capacitor would see a corresponding decrease. So it will decrease from 10 times to 10 times from C3, C2, C1, and because of the tangent of the phase shift, we need the desired 60 degree value. So the ratio will be XC to R. So tan 60 degree equals to xc divided by r. From here we can get the value of xc, that is 1.732 r. So using the general reactance formula, we can get f0, that's in the frequency, is equals to 1 by twice pi 1.732 rc. This rc will be the ratio. You see that the ratio r1, r2, r3 is 10 times higher and rc is 10 times lower for every cases. So whatever the value of r2 or c2 we can take, or sometimes we can take r1 or c1, or we can take r3 and c3, because the ratio will be same. An example: determine the frequency of oscillation of the given circuit. The circuit is given here, all the values are given for capacitor, for resistor, for op-amp, feedback and input resistors. We need to find the f0, the frequency of oscillation. So f0 equals to the law is f0 equals to 1 by twice by 1.732 rc. So for this rc, I said previously that we can take any of the branch, any of the stage. Like if we would like to take the first one, 100 nanofarad and 1k, that is taken as here. We can take also the second stage, 10 nanofarad and 10k, or we can take 1 nanofarad and 100k. So any of the one stage, this one or this one, we can take the value as r and c. So if we calculate that, we will get f0 equals to 919 hertz. Wine bridge oscillator, another type of oscillator. So you can see the circuit of this type of oscillator. So for practical cases, these types of circuit uses an op-amp, operation amplifier, and RC bridge network or RC bridge circuit. And you know that RC bridge circuit is combination of resistors and capacitors. So these are resistor and capacitor components, mainly basically fixed or set the frequency of oscillator. So you see the basic connections: resistors R1 and this R2 and the capacitors C1 and C2 form the frequency adjustment elements. So they can adjust the frequency of the circuit. And resistor R3 and R4, these two form the part of feedback path. So this is the feedback path. The op-amp output, it is connected as the bridge input at the points of A and C. C is grounded, and the bridge circuit output at points B and D. So bridge network's output is B and D. It is the input of the op-amp. So in this way, it is connected as a bridge network with op-amp. So for this circuit, the frequency output f0 is equals to 1 by twice by root over r1, c1, r2 and c2. For the wine bridge oscillator, the analysis of the bridge network results in R3 by R4 is equals to R1 by R2 plus C2 by C1. So this is the, if we neglect the loading effects, then the input output impedance will be like this one. And from here we can write the frequency, that is 1 by twice by root over R1, C1, R2 and C2. So now, if in particular cases, if the values are taken like this one, R1 equals to R2 equals to R, that's mean all are same, and C1 and C2 equals to C, then the resulting frequency will be F0 equals to 1 by twice by RC. So in that case, R3 divided by R4 will be 2. So this ratio, if it greater than 2, will provide sufficient loop gain for the circuit to oscillate. An example question is given that calculate the resonant frequency of the wine bridge oscillator of figure given below. So the circuit is given, and this is the wine bridge network. So in left portion you have the bridge network, and right portion the op-amp with all the data. That's mean the resistor values are given. So you need to calculate the resonant frequency, that is f0, and we know that if here yeah, R1 R2 is equal, C1 C2 equal, so we can use the directly the equation F0 equals to 1 by twice by RC, and this RC will be R, that is 551 kilo ohm, and C will be 0.001 microfarad. So if we calculate the value, then the result is 3120.7 hertz. Another example, design the RC elements of a wine-based oscillator for operation at F0 equals to 10 kilohertz. So frequency is given, and we need to fix the RC elements to design the whole circuit. So using equal values of RC, first we can fix the resistor value, and that is 100k, and using that value we can find the C, that is C equals to 1 by twice by F0R. So from this value we can calculate that the capacitor is 159 picofarad, and after fixing this value we can use R3, that is 300k, and R4 100k, to get the ratio of R3 greater than R4, and that will be greater than 2 times for oscillation to take place. Square or triangle function generator. So we need to build up another circuit from where we can get the square or triangular shape frequency of the output. So from this type of function generator we can create with using the integrator circuit and also a comparator. We know that the output of a comparator is square wave, and the integrator circuit's output is triangular wave. So if we pass that triangular wave into a comparator, then the output will be a square wave. So here the first part, this one, it is similar like the integrator circuit, and the second part, this one is the comparator circuit. So in integrator circuit the output will be triangle, so this portion here triangle, and this output is given on the input of the comparator. So from here it will show the output of the final in square. So in this way we can the square then drives the ramp circuit. So here the output of square triangle function generator is shown. Here you can see that two types of output. That's when the circuit produces two simultaneous outputs. One is square wave, another one is triangular wave. So square wave is swings between positive saturation V saturation and negative V saturation, and triangular wave swings to the upper and lower V upper threshold, and another one is V lower threshold. These waves have the highest peak values. Example related to the square function generator, and see the question is determine the output frequency and amplitudes for the circuit of this figure, and here we need to use the V saturation equals to plus minus 13 volt. So first note that the comparator always swings between V saturation to minus V saturation, and for that reason we need to find the upper and lower threshold voltage. So you can use this equation V upper threshold equals to V saturation R2 divided by R3. R2 here is this one 10 kilo ohm resistor, and R3 is 20 kilo ohm resistor with the comparator circuit, and V saturation is 13 volts, so you get the 6.5 the upper threshold voltage. And from this upper threshold voltage we know that the lower threshold will be minus 6.5. The next slide. So here the lower threshold will be minus 6.5. So the peak to peak value is 13 volt. As the ramp generator is driven by square wave with an amplitude of V saturation, so the equation may be written as dV by dt equals to V saturation divided by R and C. So V saturation is 13 volt and resistor value is 13 kilo ohm and C is 0.01 microfarad. So from here we can get dV by dt is equals to 39,394 volts per second. So from here we can get the time t. So t equals to 13 volt divided by 39,394 volts per second. So the time is 330 microsecond. This 13 volt is the peak to peak swing. So that 330 microsecond was for the half cycle, one half cycle. So if we want to measure the full cycle, so to go from plus 6.5 to minus 6.5, it will take the time 660 microsecond. So that's double. So the frequency f is equals to 1 by t, the time period. So we get the frequency is 1.52 kilohertz. So the result of frequency this one and the voltage amplitude was the result of this questions. Self-directed learning. So the question is explain the Barkhausen criteria. So you need to post the answer into the forum. In this week we have the forum and the assignment. So this will be the last weekly assignment for this semester. So that's all for today. Thank you.